So these were introduction of gradient, divergence and curl, and field, scalar field and curl. These were basic terminologies which you must understand briefly to learn about vector calculus. So now another terminology you will come across in vector calculus are, one is line integral, second is surface integral, and third is volume integral. You must have brief idea about these three concepts also. What are these operations? Actually these operations are vector integration, simple integration. Only special or extra thing is that they are carried out for vector field along a line, along a area or along a volume. So we will discuss these examples, these concepts one by one. So line integration, as its name suggests, name indicates that line integration is nothing but there is a vector field. There are two components. One is vector field and second is a path, a line, a curve. So line integration is found by dot product of given vector field along a line, along a curve. So what is the definition? This is also called path integration or curve integration. Line integration, path integration, curve integration, all are same. They are different names. So line integration is defined as there is a vector field. There is a vector field, first thing, and second is there is a path or line or curve, whatever you can say. These two things has to be there to carry out operation of line integration. So line integration is represented as a some symbol of integration and C. C means curve. C is written at the bottom. F, that is a function vector field into displacement vector from point A to B. So that is a path A, B. This is a path. And there is a vector field F. Vector field is there in this space. So line integration will be found by dividing this curve into small parts. So for this part, let this part, there is a small displacement vector dl. dl magnitude is equal to length of this vector, and direction for a curve, the direction will be towards tangent. Similarly for every dl vector. Sorry. So for this small displacement vector, you will find f dot product, vector dot product, f dot dl. F dot dl for this small vector. Similarly, you will find f dot dl for every division from A to B and add those dot products. That dot product from A to B is written as A to B C integration, and general term f dot dl, you have to carry out f dot dl for all these divisions. These are small dl vectors, displacement vectors, having magnitude equal to length dl and direction equal to it along the tangent. So these all dot products you have to sum up, and that sum is achieved by integration. As we have discussed in definition of integration, it is nothing but sum. So product along a path for a vector field is carried out by dividing that path into small field, and for every small division, dot product is carried out between f and dl displacement vector, and these dot products are added with this operation to find line integration. So this is a line integration, path integration, curve integration from point A to B, vector field f and dl is small segment displacement vector along this line. So all these small dot products along A to B between f and dl you have to add. So that is the definition of line integration. So we will start with why this line integration is required, what is the use of this line integration. So we will start with simple example. We know for point A to B, that is the displacement AB, and there is a force F. Work done is equal to F, this is angle theta, dot displacement vector AB, and this is equal to F AB cos theta. When displacement is straight and force is fixed, you can find work done by this simple expression. This work done is nothing but line integration of f dot dl, you can say from A to B. This is also line integration, but here we can find directly this line integral, you can find directly work done because f is fixed and AB is a line, straight line. So all those small dl vectors with dot product of all these small dl vector with f will simply add. So here you don't need not to carry out integration, you can directly find this line integration putting modulus of AB and F. This is also line integration, but it is simple because force is fixed and not changing with time or space, and displacement is also straight. Whenever any of these force is varying or displacement is not along a straight line, it is a curve, then you have to use integration. It is not any extra thing. It is simple. With this also you will find W, but when this force or displacement are not constant, then you have to find by integration method. As we are finding integration, we are using integration method in scalar quantity also, like finding volume of cone. Volume of cone is found by integration because its its volume of small discs which we create by dividing this cone into small pieces is changing. It's not constant along the length of the cone. When the things change with time or space, then you use integration, whether it is vector, whether it is scalar. So similarly, line integration is nothing but a dot product of a vector field and displacement vector when this vector field is not constant. When vector field is constant and displacement is straight, we can directly find dot product. So another example, just take another example. Let this is A, B, C, D. A, B, C, D. particle moves along AB, then BC, then CD, then DE, and there is a constant force F is equal to 5 Newton. Just assume 5 Newton along this direction. 5 Newton. So now we will find work done, which is F dot D. When particle moves along this path, so work done from AB. When particle moves from A to B, work done will be 5 into length. This is a square. Length is 2 meter. Five into 2, because force and displacement both are in same direction. So dot product will be simply their magnitude. So this is 10 Newton. Work done from BC, F dot BC. So vector BC is perpendicular to vector F, that is dot product will be 0. Work done from CD, then particle moves from C to D. Work done CD is equal to F dot vector CD is equal to, so you know vector F is in this direction and vector CD displacement vector is in this direction, reverse direction. So their dot product will be negative. So that is 5 into 2 minus 5 into 2 is equal to minus 10 Newton. And similarly work done from DA. When particle moves from D to A, work done is equal to, as this vector F dot vector displacement vector DA. So displacement vector and F are perpendicular. So this is 0. So for vector BC and CD, dot product is 0. Vector AB and vector CD, dot product is same but opposite in sign. So here you can see this is line integration. You can also say this is a line integration, but here we need not to carry out integration operation because force is fixed and this small length AB is fixed. So hence we can directly use formula F dot D. This is line integration or dot product. Line integration is nothing but addition of dot product when force or path is changing. Force is variable or path is curve. Instead of straight line, path is curve. In that case, displacement vector cannot be represented as we are representing here. AB, CD, BC. That representation of displacement vector is not possible in terms of when it is curve. So there we use integration method by dividing that curve into small dl displacement and then carry out integration operation. So here one important thing, when we carry out operation of dot product of field and displacement vector in a closed path, that is W A B C D, A B C D A, that is a closed path. This is called circulation. So we have discussed force work done for AB 10 Newton. This can also be written as integration, though we don't require integration here, but for the purpose of representation A to B, F dot dl, A to B, and here it is written C because it is a line integration, that is curve, C for curve. So when this integration is carried out in such a way, we start from a point and reach at the same point following a particular path reach at the same point, then line integration or dot product of vector field and displacement field along the closed path is called circulation. So here circulation is plus 10 plus 0, this is plus 10 plus 0, this is minus 10 plus 0 is equal to 0. Circulation is 0. Circulation is nothing but addition of dot product of field and displacement vector along closed path. So circulation is 0. We will discuss another important property of circulation. So when this path is there and it again comes A, B, particle moves from A to B and then B to A. So this is called, and there is a field F. So line integration, that is F dot dl, is represented like this. For closed path, this circle is used in the middle of this integration side, and this is called circulation. So for earlier case, rectangle, that was also integration along a closed path, and that integration was 0. It may or may not be 0. For that particular case it was 0, but it may not be 0 in other cases. So when this circulation is 0, then the field is called conservative field. And when this circulation is non-zero, that is called non-conservative field. So we can write here, for a closed path, if circulation of a field along this closed path is 0, then it is called conservative field. And if circulation of this force, that is dot product along this closed curve, is not equal to 0, then it is called non-conservative field. We will discuss this conservative and non-conservative field in detail after going through an example of line integration for variable force and curve path. So earlier case we have taken work done where force was fixed, that is 5 Newton, and displacement was along straight line, that is ABCD, that was square we have chosen. So in that case, finding dot product for different paths is easy because force and displacement are fixed, straight. But when force is variable, force is varying with in this space with its for different points, force is different, and the path of particle when it moves is not straight, it is along the curve. In that case, line integration, which is nothing but dot product of field and displacement vector along the curve, will be found by integration method. Let us discuss an example of line integration. Let there is a circle. This circle is represented as x square plus y square is equal to 1. We will discuss it in two-dimensional plane just for illustration purpose. We will not make it more complicated by taking x, y, z sphere or other surface, complicated surface. So let there is circle having equation this. So that means it's a circle of radius unity. So now there is a field F. There is a field which is given by 3xi. So you can see for different points this field will be different. When the point will change, the magnitude of this field will change. So you can say this field is in this quadrant. When we will find the field for xy point, this field is toward positive direction of x-axis, that is positive. In positive x, in this quadrant, field is toward this direction. In this quadrant, x is negative, field will be in this direction. In this quadrant also x is negative, field is in this direction. This quadrant x is positive, so with this formula field is in this direction. So here you see in all quadrant the direction of field is changing, all as well as x. When you change the point, x will change, hence the magnitude of field is also changing. Now we want to find line integration of this field along this circular curve path. So first of all, this is a point A, this is point B, this is point C, and this is point D. First of all, we will find line integration from A to B. So you can choose, so by convention, for a closed curve, by convention, always this displacement vector purpose, to find the displacement vector direction, arrow is chosen in anti-clockwise direction. This is a convention, just a convention. So now we will find line integration, that is f dot dl from A to B. Line integration is nothing but dot product of this field with small displacement vectors along path A to B. So you can say this is a force. For example, you can say this is a force in Newton, and there is a particle which moves from A to B. That particle is experiencing this force. So to find the work done by this force will be line integration FWAB, work done by this force. Work done by this force. Let a particle is moving from A to B. This particle experiences this force. There is a particle of mass m. That doesn't matter, mass doesn't matter, because we have found force. Particle moves from A to B. So work done by this force on particle will be WAB, will be line integral. Work done will be found by line integral A to B f dot dl. That is a line integral is nothing but dot product of field and displacement vector. So this dot product of field and displacement vector is used in physical quantities like this work done is one of the example of line integration or dot product. So line integration we have to find. So how will we find? So we will just take a small, at this point, take a small, just I am showing it bigger because I have to show angles also. This is length dl, this is length dl. So this vector this vector is vector dl. This is angle theta. This is a general point on this curve. This is general point on this curve. This angle is theta. And angle subtended by this dl on center is d theta. So you can see this dl vector will be along the tangent, direction of tangent in anti-clockwise direction, which is convention. So direction of tangent is this. So this dl vector will have two components, vertical and horizontal. So this angle is theta. This angle is theta. So we can say this angle is 90 minus theta, and this is vertical, so this angle is theta. And this is 90 minus theta, and this is theta. That you can work out in your notebook. How this is very simple to find the angle. You can work out in your notebook. This angle is theta from center of this dl to origin itself. Makes an angle with x-axis theta. So the angle between vertical component of vector dl, displacement vector, and tangent will also be theta. So this component is dl cos theta, and this component is dl sin theta. So we can write vector dl is equal to dl cos theta j plus dl sin theta, as the dl sin theta is negative direction, so it will be negative, minus dl sin theta I. You can write it like this: vector dl we have divided it in vertical and horizontal components to make problem easy, which this dividing in component we have for a given vector we have discussed in vector chapter. So based on that we have divided vector dl. Vector dl is along the tangent at that point. So vertical is component of vector dl is dl cos theta, and horizontal component is dl sin theta. So vector dl can be represented like this. Similarly, from simple formula of angle subtended by an arc on center, for an arc, this arc is dl. So angle subtended by an arc on center, the formula is given by dl is equal to r d theta. R is the radius of circle, and d theta is angle subtended by vector dl, displacement vector dl. dl is r d theta. That is simple formula of arc and angle subtended by that arc on the center of circle. Arc here, our radius is 0. Radius of the circle we have assumed 1, x square plus y square equal to 1. So this radius is 1. So this can be written as dl is equal to d theta. By the relation of arc and angle subtended by arc on center, we have found dl equal to d theta. So now for this small segment, f dot dl will be 3x I dot dl cos theta j minus dl sin theta I. So this dot product, this can be written, I dot j is 0, so it can be written as 3x sin theta, 3x sin theta dl here you can write parametric form. This can be written as x equal to 1 into cos theta and y is equal to 1 into sin theta. It is a parametric equation of a circle having radius r. General equation is x equal to r cos theta, y equal to r sin theta for a circle. Circle radius is 1, so here written x equal to 1 cos theta and y equal to 1 sin theta. So this dot product can also be written as x is cos theta 3 cos theta. This will be minus. Here it was minus, so this will be minus. This is minus. Minus 3 cos theta sin theta and dl. This dl we have proved that this dl is d theta. This is not vector. In vector term, this is arc dl and angle subtended by that arc. We found the relation arc is dl equal to d theta. So this can be written as d theta. So for line integration for a to b, f dot dl is equal to integration of from a to b. Theta will change from 0 to 90 degree, 0 to pi by 2 minus 3 sin theta cos theta d theta. So this is line integration of this force vector field. Force is nothing but a vector field. Line integration of this vector field along a to b. Along a to b, line integration of this vector field, and this will be minus 3 by 2 integration 0 to pi by 2. Minus 3 we have taken out, 1 by 2 we will divide, so it will be sin 2 theta d theta. So it can be written as minus 3 by 2 minus half cos 2 theta 0 to pi by 2, and this can be written as minus 3 by 2. This minus we are taking out, so it will be plus into 1 by 2 cos 2 theta 0 to pi by 2, and this is 3 by 4 cos pi minus cos 0, and this is 3 by 4. This we can write as 3 by 4 cos pi is minus 1 and this cos 0 is 1 minus 1 minus 1 minus 2 into minus 2 is equal to minus 3 by 2. So this is a very simple example. We have carried out line integration of force vector field from A to B, and this has come minus. So you can see why it is coming minus. Why it is coming minus? Because we are finding dot product of F and displacement vector. Vector F is in this quadrant is along positive x direction, and vector dl, that is displacement vector, has two components, vertical and horizontal. Vertical component will have 0 dot product with this vector, so we can omit that. But the horizontal component is toward negative direction of x-axis, negative direction. So the dot product of f dot dl from A to B will be negative, because both vectors are opposite to each other from A to B. Different segments, you will find different dl. For all dl, the vector displacement vector is in negative x direction and vertical direction. Vertical direction will have 0 dot product will have 0 with this, and negative components components in this direction, that is minus. You can see this is a minus. That is the horizontal component of displacement vector, minus. So because of this component is in negative direction and vector f is in positive direction, so both vectors are opposite to each other, hence their dot product has come minus. So this force has done, work done by this force is minus 3/2 joule if this force is in Newton and the mass of the moving particle is in kilogram, minus 3/2. So we will take another example from B to C. Now see, just see, from B to C, WBC is equal to integration B to C F dot dl. When you will find B to C, then what will happen? Whole operation is same, except in this case, in this quadrant, direction of F is toward negative side. This is direction of F, and vector dl, this is vector dl, anti-clockwise we will take. So vector dl, when you will divide the components of vector dl, it will be in this direction and in vertical downward direction. So vertical downward direction, dot product with F will be 0, and another component of displacement vector will be in negative direction, and the force is also in negative direction because x is negative. X in this quadrant will be negative. The force in this quadrant, it was in positive direction because x was positive, but in this quadrant x is negative, hence force is also negative. So force and displacement vector, horizontal component of displacement vector, both are in same direction, hence their dot product will be positive. So here what you have to change, you have to just make this as positive, sorry, this as negative and this also negative, because vertical component toward will be of displacement vector dl will be toward downward direction, and horizontal component will be toward negative x-axis direction. So downward, that is also negative, j minus j, and negative x-axis, that is also minus. So here this both components will be negative. Other operations will be same. So x, for x you need not to put x as negative. You need not to put x as negative because the limit will take care for that. Limit will take care for that. So x is a general expression, but we know that x is negative, hence we have just interpreted why this dot product will be positive, because f and dl both are in negative direction. So this will be remain same. This is minus. So that component will I will also be 0. So this will come same. This will be same. Only the thing limit is from pi to pi by 2 to pi. Pi by 2 to pi. Pi by 2 to pi. So all these expressions will be same. Just a minute. This will be solved similarly. Here, this expression at this point, you have to change limit from 0 to pi by 2 to pi by 2 to pi. Pi by 2 to pi. So this will be pi by 2 to pi. So this will be, here it will be 2 pi and here it will be pi. Only here you have to change it. Just remember, x you need not to put negative because this is general force at all points. So So the limit will take care for negative value of x. So this will be 3/4 plus 3/4 cos 2 pi is 1 minus cos pi is -1. So this is 3/4 into 2 is equal to 3/2. So from B to C the magnitude of work done is same, but only sign has changed, plus 3/2. Here it was minus 3/2. Here it was plus 3/2 joule. So you can see in this quadrant F is negative and horizontal component of DL is also negative. Both are same direction. Hence dot product is positive. And in this quadrant F is toward positive direction, whereas horizontal component of DL is in negative direction. Hence these forces are negative, so their dot product is negative. Hence this is negative. Similarly, we can say for this quadrant line integration is minus 3/2. For this quadrant line integration is plus 3/2. For third quadrant similarly line integration will be here also. This is DL, magnitude will be same, so it's horizontal component and vertical component. So horizontal component is toward positive direction, but for force is x is negative, so force will be in this direction, so it will be negative minus 3/2. And this axis DL, you see horizontal component and vertical component of DL. Horizontal component is towards positive axis and F is also positive because x is positive, so F and DL both are positive in positive direction, so their dot product will be positive. So here it will be plus 3/2. So that I have just mentioned you how this integration sign of line integration changes. So in short we can write as WAB is equal to line integral of A from A to B F dot DL is equal to minus 3/2 joule. WBC is equal to line integral from B to C, that is B to C F dot DL is equal to plus 3/2 joule. WCD along path CB is equal to line integral C to D F dot DL is equal to minus 3/2 joule. And WDA is equal to line integral F dot DL D to A is equal to plus 3/2. So in first quadrant, second quadrant line integration, third quadrant line integration, and in fourth quadrant line integration. So here you see line integration, that is work done is positive in fourth quadrant because force and displacement vector both are horizontal component of displacement vector are in same direction. So that is the sign of line integration. Now here we can see circulation. How will you find the circulation? Circulation, that is F dot D is equal to, circulation means for closed path, line integration for closed path. So that was the circle of radius 1 meter, 1. So circulation will be from here to here to here to here. crossing all four quadrants. So that is line integration from A to B f dot dl plus line integration B to C, that is A, B, C, D. Line integration from B to C f dot dl plus line integration from C to D f dot dl plus line integration D to A f dot dl. So this first is A to B. A to B is minus 3 by 2. B to C. B to C is plus 3 by 2. C to D. C to D is minus 3 by 2. And D to, sorry, this is D to A. D to A. D to A, it is plus 3 by 2. This is 0. So we see here the circulation, that is line integration along closed path for this force which is given by 3xi is 0. That means this force is a conservative force. Whenever circulation or in line integration of a vector field along closed path is 0, then vector field is called conservative. So that was the line integration, introduction with line integration. We have discussed till now. In normal integration, we have a function and we integrate that function under certain limits a to b. Whereas in line integration, just see the difference. We have a function, vector function, which was 3xi, first thing, and second thing, we have a curve, equation of curve, that is x square plus y square is equal to 1. We have two things, equation of curve and equation of vector field in line integration. Whereas in normal integration, only we have equation of function and limit from a to b. Additional thing is line integration is equation of curve. So along this curve, this dot product of vector field is formed. So now we will discuss another important property of line integration. So we know, we have learned in gradient topic that gradient of a field is equal to is a vector field. Gradient of a field is a vector field. So let us find circulation. Let us find line integration of a gradient field. So because it's a vector field, so line integration of this vector field can be found from A to B. Line integration, we must have a vector field and a curve, equation of curve. So gradient of a function which we have discussed is a vector field. So this vector field, line integration of this vector field along a curve, let this is a curve from A to B. A to B. We have also discussed that this gradient is analogous to derivative. So what is the fundamental theorem of calculus? Fundamental theorem of calculus for normal calculus is A to B f dash x dx is equal to fb minus fa. That is fundamental theorem of calculus. This is the derivative of function fx. F dash x is derivative of fx. So in normal calculus, we know f dash x dx, derivative of a function. To find the definite integration, we must have antiderivative, that is fx. Antiderivative of f dash x is fx. fb minus fa. This is the fundamental theorem of calculus. Fundamental theorem of calculus. Analogous to this fundamental theorem of calculus in normal terminology, in vector form, this is derivative, that is, this is also derivative in normal calculus, and antiderivative is fx. Similarly here, del f is also, grad f is also derivative of function f, that is scalar function. So this theorem can be written as f b minus f a. Here f is a vector function for which we have found grad, which is f is a scalar function. We have found gradient of f, that is vector function. Now line integration of this vector function, that is gradient of f along a to b, will be fb minus fa, because normal calculus antiderivative, we find antiderivative of function to find definite integration, and this formula holds true for vector calculus also. Hence this equation is called fundamental theorem of vector calculus. This is fundamental theorem of calculus for normal functions, and this is fundamental theorem of vector calculus for field functions. So what important inference we find from fundamental theorem of vector calculus? Line integration of a gradient is property of endpoints only. Property of endpoints. It doesn't depend on path. For a closed loop, A to A, this will be fa minus fa is equal to 0. Hence, line integration of a gradient function is always 0 for a closed path. That means gradient circulation of gradient is always 0. Circulation, that is for closed path, line integration of a gradient function is always 0 by fundamental theorem of vector calculus. This means that gradient of f is a conservative field. Because its circulation is 0. Circulation of a gradient function is 0. That means gradient of a function is a vector field which is a conservative vector. This is a very important theorem. So this, for example, gradient of gravitational potential energy will give you gravitational force function, and gradient of electrostatic potential energy will give you electric field. So that is the use of gradient function. of gradient, we will just discuss physical use of gradient, physical application of gradient, where you know the potential energy. There is a mass m. This is mass m at point r, distance r. So let us assume that this point mass m is kept at the origin. So we know from Newton's law the potential energy of unit mass. Potential energy of unit mass at point P is G m by r. There is a simple formula of potential energy, G m by r. So we will find gradient of potential energy, and we will show that gradient of potential energy is gravitational field. So this potential energy at point P is given by this expression. Function point P coordinate are x, y, z. So this can be written as minus G m by under root x square plus y square plus z square. U. Now we will find grad of this. Grad of U is equal to del U. Just use the expression of del. You can see minus Gm. This is potential energy for a unit mass. Due to this concentrated mass, there will be a gravitational field. For a unit mass placed at this point, 1 kilogram left, 1 kilogram. Unit mass, potential energy is given by this expression. So, gradient of this potential energy is minus Gm del x and 1 by under root x square plus y square plus z square into I plus del y under root x square plus y square plus z square into j plus del z 1 by under root x square plus y square plus z square k. This is grad U, gradient of potential energy function. So we will find it minus Gm. Now partial derivative of under root x square plus y square plus z square is minus 1 by 2 x square plus y square plus z square minus 3 by 2 power minus 3 by 2 into 2x I. That was partial differentiation with respect to x for this function. Similarly, minus 1 by 2 under root x square plus y square plus z square, x square plus y square plus z square per power minus 3 by 2 into 2y j plus minus 1 by 2 x square plus y square plus z square power minus 3 by 2 2z k. So we have partially differentiated this potential energy function. We got this minus Gm. This minus is everywhere, so you take this minus out, so this will be plus 1 by 2. Everywhere this 1 by 2, cut it. This 1 by 2, this 1 by 2. So this function will be reduced to x by x square plus y square plus z square power 3 by 2. I plus y by x square plus y square plus z square power 3 by 2. J plus z by x square plus y square plus z square power 3 by 2. K. This is grade U. Gradient of potential energy. This can be written as Gm by x square plus y square plus z square. It can be written as xy under root x square plus y square plus z square I plus y by under root x square plus y square plus z square J plus z by under root x square plus y square plus z square K. X square plus y square plus z square is nothing but distance r from origin end point. We can write it r square, and this vector is nothing but vector OP by mod of vector OP. This vector is xy under root x square plus y square plus z square I plus y under root y square plus. This is unit vector of position vector in the direction of vector P. If you will find unit vector in the direction of P, that is unit vector in the direction of vector OP, that is the unit vector. Because this under root x square plus y square plus z square is modulus of this vector, and xi, yj, zk is position vector OP. So I will just write vector OP is equal to xi plus yj plus zk, because point coordinates of P are x, y, z. Vector OP is this. So unit vector along OP is equal to vector OP by mod of vector OP, and this is xi plus yj plus zk divided by under root x square and y square plus z square. That is same thing. You can write it like this: Gm by r square xi plus yj plus zk divided by under root x square plus y square plus z square. So this is unit vector. This can be written like this. So this is Gm by r square, and unit vector, I will write unit vector along OP as using cap. So that is G. You know, by Newton's gravitational law, gravitational acceleration is given by this expression. So we have found here that when you find gradient of potential energy, we got gravitational acceleration expression. We got a vector field. This is a vector field, vector OP. This is vector OP. This is vector, unit vector OP. So this G is a gravitational acceleration, is a vector field which has been derived by finding gradient of potential energy due to this mass m at point P. when you find gradient of potential energy field, that is scalar field, you find gravitational field, you find expression of gravitational field, which is vector field. So this is another example that gradient of a scalar field is always a vector field. So here we found this vector field, that is gravitational field G, by finding gradient of potential energy field, that is scalar. Just recall our earlier example of potential energy function minus G m by r square. We found grad of u that we have found by vector calculus, vector formula, that grad of u is equal to G, and it was, sorry, this is R, potential energy, this is R, and this was G m by r square into unit vector. You can say in that case we have found unit vector OP, so that we will denote here radial unit vector in radial direction. So grad of this potential energy function, that is scalar function, we have found earlier example, it was equal to gravitational field. That grad was equal to gravitational field, and that gravitational field was represented by, sorry, this is r square. It was represented as Gm by r square, and direction was along radius, and this is unit vector along general point P, from mass m. So one important thing, because gravitational field has been achieved by finding gradient of potential energy, and what we have proved right now, gradient is always a conservative force. Gradient of u is a conservative force by fundamental theorem of vector calculus. We have proved it. Gradient of a field, scalar field, is always a conservative vector. G is gradient of potential energy. That means gravitational field is a gradient of potential energy. Because this gradient field is conservative field, hence G is also a conservative field. That means gravitational force is a conservative force. What is conservative force? Along the closed path, its circulation is zero. Or from point A to B, when particle moves from point A to B under this force, work done depends only on end points, that is A to B. A to B or B to B, not on this path. For a conservative vector field, work done depends only on end points, not on nature of path. For all these paths, work done is same. And for closed path, work done is zero. That is problem. So in the gravitational field, you know, this is point A, this is point B, and there is a gravitational field. Particle goes from here to here. Work done is, there is some work done from A to B. Particle goes by this way, particle goes by this path, particle goes by this path. Whatever path particle is choosing, because G is a conservative vector field, hence work done by this gravitational field will depend only on end points, position of end points, not on the path followed. Similarly, for any closed path, A, D, for any closed path, work done or line integration, that is circulation, is equal to 0 for a conservative field. As G is a conservative field, and for gravitational field also, work done in a closed path. When particle moves in a closed path, when particle moves and comes again at its original path, original position, then work done will be 0, because line integration, that is circulation of this conservative force, is always 0 in a closed path. So that was about conservative field. Now there is another theorem that for a conservative field, curl is always 0. If curl of a vector field is 0, then F is also called a conservative. F will be a conservative field. F will be conservative. Or we can say, we have also defined that if curl is 0, it is irrotational. It is also called irrotational field. And by this theorem, conservative vector field, for a conservative vector field, its curl is 0. So it can be said that all irrotational fields are conservative fields. So that is, curl of vector field is equal to 0, then F is conservative field, or F is also irrotational field. Irrotational field. Curl is 0. If curl is not 0, then F is non-conservative field, or you can say F is rotational field. This is based on curl. For a conservative field, curl is always 0. So we have discussed few problems and few concepts of line integration. I will summarize all those concepts. First is, grad F is a conservative vector field. Gradient of any scalar function is a conservative vector field. As G is equal to gradient of potential energy, hence, because gradient is a conservative field, hence G, gravitational field, is also a conservative field. Similarly, electric field also, you will prove E, that is electric field is equal to grad of electrostatic potential energy. Hence E is also, because grad has been achieved by derivative of a scalar field, and grad is also always a conservative field, hence E is a electric field is also a conservative field. Second, for a conservative field, if curl of a field is equal to 0, then also F is conservative field. But you must remember that reverse is not true. That is, if curl of a vector field is not 0, then it is not necessarily a non-conservative field. But if curl is 0, then definitely F is a conservative field. If curl of a vector is 0, it is conservative and also it is irrotational. And if curl is for a field is not 0, it is called rotational vector, rotational field. So that is the main principle, main theorem of line integration, and also for a fundamental theorem we have discussed fundamental theorem of vector calculus, that is for a grad f dot dl is equal to f p minus f. This is fundamental theorem of vector calculus and analogous to fundamental theorem of calculus, which is written as f p minus. F is antiderivative of this function. Similarly, this is gradient, and we have said that gradient is also derivative of its gradient, because del y, del x, del y, del z, we use grade to find gradient. So this is also derivative, analogous to derivative. So this was derivative of fx. Similarly, this is derivative of fx. Hence, this theorem holds true for vector form also, similar to normal calculus. So fundamental theorem of calculus, fundamental theorem of vector calculus. Because of this theorem, gradient is a conservative field.